In lectures we have been working our way through this section on second order ODEs, second order ordinary differential equations. And we've motivated the study, we've looked at some basic solution methods to homogeneous or homogeneous problems where you have 0 on the right hand side. In today's lecture we're going to look at the so-called inhomogeneous or non-homogeneous case and discuss a method of undetermined coefficients. So some of you will have seen this before, but my aim is to refresh your memory, and my aim is to also show you why the method works. So that's the objective of this first lecture, to cover this subsection here. Now, in previous lectures we've discussed the following second order ordinary differential equation with constant coefficients, a, b and c just numbers, and a 0 right hand side. Now, to sort of simplify and compact the notation, I've introduced this operator L, which is just a linear operator. Okay, so think of y as a function here, a twice differentiable function. L takes that function, differentiates it once, differentiates it twice, and then spits out ay double prime plus by prime plus cy. Now, the subject of this lecture is to discuss this more general case where you have a given function of x on the right hand side. So think of g of x as something like x squared, or e to the x, or 2x plus 1, or cosine x, something like that. Okay, well, the general solution, note that I've changed these numbers here. You want to make sure that you have a 2 here and a 1 here and a 2 here. I think in your copy they're round the other way. Okay, so we want to make sure this is a 2, this is a 1 and this is a 2. Okay? Now what does this theorem say? Well, essentially it says that to construct a solution to this more general problem 2, what you do is you solve this simpler problem and construct a solution to the simpler homogeneous problem 1, denote that solution by y sub h, and then you build or you construct another solution to 2, a particular solution that you construct, y sub p, and then add the two things together. Okay? So this form is extremely important. The general solution to this problem is the solution to this simpler problem plus any particular solution that you like to construct to equation 2. Well, why is that true? Well, let's try to interpret it before we actually see why it's true. Essentially, the result says that all solutions to the more general problem have this form. Now, we know from the previous lecture that the solution to the homogeneous problem, every solution to the homogeneous problem, y sub h, can be written as a linear combination of two linearly independent solutions, y sub 1 and y sub 2, and c1 and c2 are constants. Okay? Now, if we know all solutions to the homogeneous problem, then to construct all solutions to the non-homogeneous problem, all you have to do is produce one solution, y sub p, one particular solution to the more general problem, and then combine it with y sub h just by adding. Okay, well, why is that true? Some of you may know that that's true and be looking at and saying, well, hang on, well, I know that. That's good. But why is it true? Okay, well, suppose y is any solution to the non-homogeneous problem 2. and let y sub p be a known, a constructed particular solution to the non-homogeneous or inhomogeneous problem. If you look at the difference between any solution and your particular solution, and you operate L on it, then L is a linear operator, so you can break that up, and you know that this equals g of x and this equals g of x, so the difference will just be 0. So what does that say? It says the difference of these two solutions to the inhomogeneous problem is a solution to the simpler homogeneous problem. So what does that mean? Well, it means that this difference can be written as a linear combination of y1 and y2, where y1 and y2 are linearly independent solutions to the simpler homogeneous problem. So let's write that down here and then just rearrange it. Take that to the other side, and that's my y sub h, so I get the following. Okay? So that's now you know why you take the solution to the homogeneous problem and add a particular solution, any particular solution to the non-homogeneous problem, and add them together. Okay? That's why it works. Now, the big question here is, well, this sort of method here involved us producing or constructing a particular solution to the non-homogeneous problem. Well, a good question is, well, how do we do that? How do we do that? Well, I'm glad you asked. How do we construct a particular solution? Now, there are a number of methods available to do this. And one reasonably simple method is to assume this constructed solution, this y sub p, this particular solution, is in a similar form to the right-hand side. So if this is a polynomial, you would assume this to be also a polynomial. Okay? If this is an exponential function, you would kind of assume this to be also an exponential function. Now, again, I'm sort of speaking very loosely there. There are little tweaks and whatnot. Now, this approach will work if the right-hand side of your equation is not too exotic. So, you know, if g of x is like a combination of exponentials, quadratics, trig functions, or sine and cos, then the method that I'm going to show you today will work, and we call the method of undetermined coefficients. Okay, now here's a big table for your inhomogeneous problem, and basically here are different versions of your right-hand side function, and here are different choices for what particular solution, your constructed solution. But this is, you know, this is a lot of information here. So it's more of a reference guide. The best way to, in my opinion, the best way to get good at these problems is just do a few of the problems and see the method firsthand. Okay, so this is more of a reference table. You'll come back to it after you get a feel for the solution methods. Okay, so here's a basic problem. In this particular example, the right-hand side is your given function, g of x, 2x plus 3. What we would like to do is solve that more complicated problem for the unknown function y. Okay, so it's a two-step process, I guess, maybe a three-step if you really want to add some things. So the solution to this, now you might want to draw sort of a two-column thing here because there is a little bit to write in here. So I'm just going to use a capital H here, y sub h plus y sub p. Y sub h solves the homogeneous version of star, and Y sub p is a particular constructed solution. That's what the P stands for. Okay, so let's just do this, and we will solve Y sub h, we'll construct Y sub p, and then we'll add them together. Okay. So we're going to solve the homogeneous version of star. So I forget about the right-hand side. Essentially, I just change it to 0. And now I have a differential equation there that I know how to solve. Remember from a previous lecture, we know that the analysis of this particular differential equation is just reduced to a quadratic equation based on the coefficients. Okay, so this has the characteristic equation. What is it going to be? It's going to be r squared minus 5r plus 6 equals 0. So what I can do is factorise that in this case, and then look at the roots. So let's factorise this left-hand side. So my numbers are going to be something like minus 3 and minus 2 in my factorisation. So the roots are going to be positive 3 and positive 2. Okay, so we look at the roots. They are both real numbers and they're unequal. Therefore, Y sub h, the solution to the homogeneous problem, will have a special form. So the roots are real and unequal. So Y sub h has the following form. Okay, R1 and R2 are just the roots. A and B are just constants. Okay. Now it doesn't matter which way you put in the R1 and the R2. It's just a general solution. Okay, so that's pretty easy, right? As long as we can solve a quadratic and analyse the roots, we can come up with our homogeneous solution to this problem. Okay, the slightly more difficult part is constructing your Y sub p. Okay, now what we're going to do is look at the form of this g of x, this right-hand side, and choose Y sub p to be of a similar form. Okay, so let me show you. This is like first degree polynomial, 2x plus 3, just some sort of linear type function. Let's choose Y sub p to be of the same form. Okay, let's say cx plus d, where c and d are just constants that we want to determine. Okay, so how do I do that? Well, any particular solution to the original problem star must satisfy the equation. So what I'm going to do is I'm going to start with this, I'm going to differentiate it once, differentiate it twice, and sub into star. And then I'm going to equate the coefficients to find c and d. Okay, I want to determine the constants, the coefficients c and d in the bottom line. That's why it's called the method of undetermined coefficients, right? So if I differentiate this, I'll get c. And if I differentiate again, I get 0. Okay, so let's back substitute into the starred equation. Okay, we're going to form the following. So wherever we see y, we're going to replace it with cx plus d. Wherever we see y dash, we're going to replace it with c. And wherever we see y double dash, we're going to replace it with 0. So star is going to become 0 minus 5c plus 6 times this equals 2x plus 3. Okay, so all I need to do now is equate the coefficients. So what's c going to be? Well, we're going to, from the coefficients of x, we're going to get 6c equals 2. And if we equate the constants, minus 5c plus 6d equals 3. So we equate the coefficients. To obtain the following. Okay, so we're going to get 6c equals 3 and minus 5c plus 6c equals 2. Let me adjust that. And minus 5c plus 6d equals 3. So we've got some basic equations there. Obviously c is going to be something like a third. And I can get d from the other one. Okay, d 7/9 according to my calculations. Okay, so now for this particular solution, we've constructed the c and d so that this will actually be a solution to star. One third. Okay, so there's my particular solution. There's my solution to the homogeneous problem. All we do is we take those two and we add them together to form the general solution to my original ODE star. So if you like, this is like a third step. Okay, so it's this. Okay. Now, when you're doing the, doing these kinds of questions, of course, you don't have to put all this detail in, but I've just put it in to explain it as I solve it. All right, here's another one where the right-hand side is not a polynomial, but it's a exponential function. So how do we handle that case? Well, I'll do this one a lot quicker because if you look carefully, the resulting homogeneous problem, the left-hand side equals 0, is the same. So I don't have to, for this problem, I don't have to go back and do all this stuff again. Okay? Okay, so here, the form of my right-hand side has changed to an exponential function. So let's call that star. From the previous example, y sub h is just the following. Okay. So I don't really have to worry about writing that out. Here, big A and big B are constants, arbitrary constants. So how do we construct a particular solution? Okay, so we look at the form of g of x. It's an exponential function. And what I'm going to do is use that to construct the form of my y sub p, my particular solution. Okay, so I'm going to keep the 5x, but just have a constant times e to the 5x. Okay, so you want to keep the 5x, but just have an arbitrary constant at the front. Okay, so what I would like to do in this second step is determine the value of c, such that this particular constructed solution will satisfy the original equation. Okay? Okay, so let's just differentiate once. I'll get 5c e to the 5x. Differentiate twice. I'll get 25, so that 5 comes to the front again. 25c e to the 5x. And what I'm going to do is sub in these three functions into star, and then I'm going to equate the coefficients and find the value of c. That makes this a solution. We substitute into star to form the following. Okay, so y double prime, we replace that with this, 25c e to the 5x, minus 5y prime, well, it's just minus 5 times that. Oh, so that'll be a minus 25. And plus 6y. So we're going to get the following. And the right-hand side is just 12 e to the 5x. So you can see these first two terms are going to cancel off, and I get the following. So again, if I equate the coefficients, big C is going to be something like positive 2, right? What's that? Not something like Hence, big C equals 2. And so, what's our C here? It's 2. So I'm going to get 2 e to the 5x. So, we've got our homogeneous part. We've got our particular solution. So let's just add them together. So I'm going to get something like a e to the 3x plus b e to the 2x plus 2 e to the 5x, where a and big B are constants, arbitrary constants. Now, can we determine big A and big B? We could determine that constant big C in there, but can we determine big A and big B? No, why not? Yeah, we don't have enough information. If we had some initial conditions, some extra information, coupled with star, then we could go back and, you know, use this to determine big A and big B. Okay? So let's say you got down to this part and, you know, you couldn't balance these things by choosing a value of C. Okay? Sometimes you'll get down there and you just can't solve. You can't find a value of C that will satisfy the thing. What does this mean? Well, it means either you've made an incorrect construction, starting with your y sub p, or you've differentiated wrongly. Okay? Any other questions so far? Okay. Now, I think you've got a 12 here. I've got a 10, so make sure you change that. Now, this is a good question to compare it with what we've done before. Let me just put this back for a second. What happens, right? You can see when I add this solution with this solution to form the general solution, this is adding something new to this, okay? If this was an e to the 2x or an e to the 3x, it's already contained in this homogeneous solution. So if I was to add them together, this part wouldn't be adding anything new. It wouldn't be bringing anything new to the table. This is something you need to be conscious of, and in fact, it's covered in this particular example. So this is a very good example. Okay, again, the homogeneous solution is very easy to calculate because we can just take it from the previous example. So here we've got a right-hand side that is, again, an exponential function, but as we'll see, a little bit of care needs to be taken here. So from the previous exercise, y sub h is something like this. Okay, that solves the homogeneous problem. Now, the right-hand side is 10 times e to the 2x. Now, so from what we looked at in the previous example, what would you expect a good choice for y sub p to be? Well, it'd be something like this, wouldn't it? If I'm going to construct a particular solution, wouldn't that be a good form? But wait, I'm confused. If that is already sort of contained in there. So if I add these two things together, this construction is not bringing anything new when I add them together. Okay? Look carefully, the y sub p, the e to the 2x part, is already contained in y sub h. So if I were to add these two solutions together, y sub p would not be bringing anything new. So this is not a good choice. No. Because y sub p is already contained in y sub h, and so it doesn't bring anything new. Okay, so what I'm going to do is multiply that y sub p choice through by x. Now we've seen this in a way when we looked at the homogeneous problem with real and repeated roots. We had one exponential plus x times another exponential. So you can kind of think of this as an informal analogue of that. So let's try the following. Y sub p equals cx e to the 2x. Now, is this contained anywhere in here? Well, no, it's not, because you've got this x multiplying through. Okay, so let's differentiate this once, differentiate this twice. You need the product rule. So if I differentiate this once, my calculations give me the following. And if I differentiate it twice, again, my calcs give me the following. And what you want to do is take those three expressions, sub them into star, and then compute C. Okay, so we're going to have something like this. C e to the 2x times 4 plus 4x minus 5 times this plus 6 times this. Oh, yes. Okay, so a little bit of algebra is required and x times e to the 2x will all cancel out when you expand that. So we're going to get 4c minus 5c is going to be something like, yeah, minus c equals 10, right? Just by equating the coefficients. So hence, this is going to be something like minus 10x e to the 2x. Thus, we add our two solutions, or our two functions, and add and that's the general solution to our original problem. Okay. All right, so the important thing there is you want to make a, assuming you can do the algebra, the important thing is you want to make a good choice for y sub p, a good construction, right? You want to make sure that whatever your construction is, it is not contained in this, okay? This is not contained in this, okay?
What if the homogeneous problem you had like ae2x plus bx2?
Oh, good question. Yes. Okay, so that's a very good question. What happens if I tried this and this was already in there? What do you think I would do to this? Multiply it by x again. So you'd have an x squared in here. Okay? So I've given you some, so you'd keep multiplying your particular solution through by x or t or whatever the independent variable is until it's no longer in the homogeneous solution. Okay? Why does the method work? When I say that, why can I construct a particular solution just from based on the form of g? If g is an exponential, well, I'll just make my construction an exponential. Well, that's a very good question. Some of you may know how to do this process, but why does it work? This is the original example that we looked at. The right-hand side is like a linear type function. What we do is, suppose y sub p is a solution to this. We don't know what it is, but let's just try to construct it. What I can do is differentiate the original ODE in some way that annihilates the right-hand side. Okay? If you look closely, 2x plus 3, if you differentiate that twice, it gets annihilated to 0. It disappears. So what I can do is introduce a new linear type operator, m, just in this case defined by this. And if I take, basically, if I differentiate twice both sides of the equation, I'll get this particular problem. Now, this particular problem, it's a higher order problem, fourth order. It's linear and it's got constant coefficients. Now, we can solve that just by the methods that we already know. The only difference is our characteristic equation is going to have a higher degree. It's going to be involve something like r to the power 4. Solve the characteristic equation, you get the following roots. You get 0 as a repeated root, positive 2 and positive 3. So the basic theory says that a solution to this homogeneous problem will be something like this. Now, this and this are already in the homogeneous solution, so I can forget about those, right? So what's left? This, cx plus d. You see how that and that have the same general form? So there are constants, in this case c and d, such that you can assume a particular solution has that cx plus d form. Okay, very powerful method known as the annihilator method. Okay, you annihilate the right-hand side until it disappears. Now, the choice of annihilating operator here, the choice here is dependent on this. So if this was e to the x, you would choose m of y equals y prime minus y. Because you know y prime minus y, if you know e to the x satisfies that. Okay? So this is why the method of undetermined coefficients only works with certain kinds of functions on the right-hand side. You can't annihilate all functions, okay, through differentiation. Okay, think of tan x. How would you annihilate tan x through differentiation? You can't. You can't do it. Okay? So this is why we say our right-hand side's thick. It means that when we say that, it means that we can annihilate it through some sort of linear differential operator with constant coefficients.